So we talked about boosting and about some ways of understanding boosting. And now we want to start looking at how do you actually do boosting. So to use boosting, you need to use some kind of weak learner. And what should the weak learner be? There are many, many options. And it's a priori not immediately clear what you should use. So I'll just show you some options that are popular. That is not to say that this is the only way to go. You can invent your own. Okay. So here are some styles of weak learners that are popular. One is very, very simple. It's stumps. So these are decision trees that basically have just one decision rule at the top, and then they have two options, yes and no, one going to minus here and one going to plus. Okay, so that's one possibility. And when you have a decision rule like that, you get a weight for it. You get the alpha that multiplies it. And so here is the alpha. Now, interestingly, you can actually make it even simpler by splitting it into two parts. So you can have one rule that says if the season is summer, then I do plus, and then another one that if the season is winter, then I do plus. And each one of them gets an alpha. Maybe this, if it was this alpha originally, then it's alpha here and minus alpha here. So what would you say? Why is this worthwhile? This is worthwhile because here I'm basically using two rules that are exactly complementary. But it's sometimes useful to have rules that are not complementary. So basically to say, under some conditions, I make a prediction. Otherwise, I make no prediction. That is what I call a specialist. Okay, so this is a generalist because it always makes a prediction. And these two are each specialists. And in a way, specialists are much more flexible because they are required to make a prediction only on a small subpart, and on the rest of the space, they say nothing. Another style that is very popular is to use boosting on top of decision trees. So here, our weak learner is not just a stump, but it's a bigger decision tree, maybe fully grown, maybe not fully grown, but in any case, more complex. So the weak learner in this case is actually not that weak, but experience has shown that using boosting on top of decision trees improves the performance significantly. And then, other than that, you can almost use anything. So people have used neural networks, nearest neighbor, naive Bayes, almost any kind of learning rule that you can think of or classification, people have tried to use it. So what really would work is maybe up to you. But this style of classifiers is already very general and useful for many cases. And you have a lot of implementations of that. So I'll tell you now about a slightly different decision or classifier that is in a sense a combination of boosting and decision trees. So if you remember, when we talked about decision trees, one way of thinking about it is as a partition of the space. Okay, so here is a partition of the space that corresponds to a simple decision tree. And the first thing we want to do is we want to figure out how can you represent this tree as a boosted sum of weak rules. Okay, so initially this might seem completely impossible, but it's actually quite simple. So here is how we do it. We start with a rule that is universal, that it holds everywhere, and we find the alpha for that rule, and that alpha we put at the root. Okay, so that basically is a prediction that we make even if we don't see any value of x or y. Then we use the first splitter, and the first splitter is itself a weak rule, right? So it might have some weight, and this weight associates minus 0.1 here and plus 0.1 here, and that gets added to what we already have. So it looks something like this. Okay, so we add plus 0.1 here, and minus 0.1 here. And now we split on the y, and we get another two terms. Here we basically found a separate alpha for the no and a separate alpha for the yes. So the two alphas basically gave us these contributions to the prediction. And now if we sum them, we get the values that are the sum. And if we take the sign of that, we revert to the original decision tree. Okay, so basically what I showed you is how you can think about decision tree and also decision tree learning as simply a process in which you're doing boosting. But the special thing is that the rules that are not right at the root, they are by definition specialists, because they apply only to subpart of the data, and on the other part here, they say nothing. Okay? So this is how you would represent a tree using boosting. And the question is, why is this worthwhile? Well, it's worthwhile because it lets us generate structures that are much more general. So here is an alternating decision tree. Okay, so we built first a decision tree, just like we did before. And now, when we're looking for where to add a new weak rule, we don't necessarily have to add it only in the leaves, right? We can add a weak rule here, we can add a weak rule here. Okay, so if we add a weak rule here, let's say this one, then it basically checks whether y is smaller than 1. And in that case, it contributes plus 0.7. If no, it contributes nothing. So what does that give us? It gives us something like a split here that adds 0.7 to the score. And now if you take the sign of that, then you get this kind of rule. So this kind of rule is not exactly easy to represent using a decision tree, but using this kind of alternating decision tree, it's quite easy. And why do I call it alternating? Because we have alternating levels. You have on the odd levels, you have contributions to the score. And on the even levels, you have the inequalities. So if you want to calculate the score for a particular place, you start at the root, and you go to every one of the children of the root, and then you go only to the child that is corresponding to the condition. And you continue like that recursively. Then you sum all of the elements in the nodes that you reached, and that is your final score. The sign of that is your prediction. Okay? So these are alternating decision trees, and this is how boosting can be used to learn them. So here is an example just to show you that this is actually sometimes a very reasonable way to make predictions, that it gives you small but very accurate rules. Okay, so this is a very small data set. It's the UC Irvine, it's a Cleve data set from UC Irvine. Basically, it has to do with heart disease diagnostics. You have +1 is healthy and -1 is sick. And 13 features that were taken from test when the person got into the hospital. Okay, so you need to take these features and decide whether or not they have heart disease. So we have not a large number of instances, just 303. And let's see what is the alternating tree that we got. So this is the alternating tree that we got. And what you see immediately is that the rules at the first level, there are many of the rules that are just right now at the first level. And then there's a few rules that go to the second level. Even more than that, if you look at the numbers here, 1, 2, 3, 4, that's the order in which these splitting nodes have been added. So initially it just added these 4, and then it added this 5 and this 6. Okay, so that shows you that these 4 are really a very good representation. And why does this make sense, or why is this better than just using a decision tree? Because all of these indicators here, they basically give us independent evidence. We want to look at each one of them and say how much does it contribute to the chance that this person has a heart problem or doesn't have a heart problem. And what a tree allows us to do is only to go on one of them and then at the leaves of that check for another thing. So you could translate that into a tree, but it would be a pretty big tree. So here are actually a comparison of this on this data set of different algorithms. Here is AD trees. Here is C5.0, which is a tree learning algorithm. Here is C5.0 plus boosting. And here is boosting stumps. Okay, boosting stumps is basically what we saw before, is just using the simplest kind of one-level trees. And what you see is that the smallest one in terms of number of splits is the AD tree, which makes it the easiest to understand because there's less rules to interpret. And its error is, test error is very good and doesn't fluctuate too much. This is the variation of the test error. And C5.0 is much bigger, but much worse in performance. C5.0 plus boosting is even bigger than that and better than C5.0 by itself, but not as good as just AD trees. And then boosting stumps is actually slightly better than AD trees, but it requires more splits. Okay, so the two-level splitting is actually beneficial here. So you see that this is another approach to how to build a decision tree or a combination of decision trees. In some cases, at least, it works very well. Okay, so to summarize, almost anything can be used as a weak learner. And some popular choices are boosting trees and boosting stumps, okay, which is also boosting trees, just trees with one level. Okay, those are the popular ones. Those are the ones for which you can find a lot of software. There's many other possibilities. And alternating decision trees, they basically combine the idea of averaging that boosting gives you and the idea of splitting that decision tree gives you in kind of a recursive structure that can capture a lot of information in a small number of splits. And it can therefore be good in representing both independent features, so features that give you independent information, and that basically would be represented as averaging them, or dependent features where you want to check on feature 2 only after you know if feature 1 is, let's say, smaller than some threshold. So next we're going to talk about boosting and overfitting. See you then.